And welcome everyone. Thank you for choosing to take some time today out of your schedule to attend our webinar on online monitoring of nitrate with optical sensors for wastewater process control. On the title screen here, we've got an image on the bottom right, an aerial view of the Littleton-Englewood wastewater treatment plant in Colorado, one of our biggest IQ SensorNet customers, and a customer that has chosen to trust their critical nitrate monitoring measurements to an optical nitrate sensor. A zoom-in close-up of their nitrate sensor is shown in the left panel. You can see that the sensor has been pulled from the sample and is quite muddy and murky. It's a tough environment. But in the middle there, where the measuring occurs, is very clear. And that's on account of an innovative cleaning system offered with this particular probe, which we'll talk about in more detail later on in the webinar. The topics we'll cover will include measurement principles of optical sensors, the design features of an optical sensor, applications of customers who have used optical sensor for nitrate monitoring, and then we'll also talk about we'll compare and contrast optical nitrate sensors with the alternative ion selective electrode nitrate sensors. Optical sensors measure light intensity. If we were to place our sample between a lamp and a detector and turned on that lamp, which shined light on the sample with a given intensity, it would be normal to expect that some of that intensity would be decreased after entering the sample, so that what reaches the detector is a lower intensity than the light originally emitted at the lamp. Mathematically, we can calculate what the transmission of that light is as the intensity at the detector divided by the intensity of the light leaving the lamp. It is customary to express this in percent form, so we can get percent transmission by multiplying that by 100. For analytical purposes, the two main principles that govern light transmission can be explained by a combined Beer-Lambert law. First off, the Lambert law states that intensity decreases exponentially as the length of the optical path length, that is the distance between the sample and the detector, increases. And this is illustrated here in this picture. If we had broken our sample into 3 equal-sized cuvettes with the same sample, we would find that one is each cuvette absorbs the same equal proportion of light as each other cuvette. We'd also find that as the number of cuvettes, say if we increase this from 3 up to 4 or 5 or 6, as those increased, the intensity at the detector would be less or lower. The other principle is then Beer's law. And Beer's law states that the intensity of light decreases exponentially as the concentration of the sample increases. So in this example, if we had, say, 3 standard concentrations, and we carefully selected those 3 standard concentrations, so each successive standard absorbed 50% of the light as the preceding sample. And if we measure these in series, one after the other, and through the first sample, the intensity would be 50%. Through the second sample, the transmission would be 25%, and then through the third sample, 12.5%. And then if we took this and plotted that transmission versus concentration, we would get an exponential curve as we predicted. It's very handy to know, but it's not so useful for making a measurement. So instead, we have another parameter called absorbance. And absorbance is calculated as the log. You take the log of the initial intensity over the intensity at the detector. And by doing this with the same three samples, we would find that the intensity through the first sample would have an absorbance of 0.301. And then through the second sample would have an absorbance of 0.602, and through the third sample an absorbance of 0.903. In doing so, we've created a linear curve that relates the absorbance of the sample to the concentration in a straight line, making it convenient to calculate the concentration of your sample. When it comes to wastewater samples, there are a lot of things we need to measure. And so if we look at this chart here, it shows the light absorption versus the wavelength of light from 200 nanometers through 720 nanometers. And we see that in certain regions, for example, you'll have regions dominated by the absorbance from nitrate or from organic contamination, COD in other words, or turbidity, or TSS in other words. Also, you'll see that the parameter spectral absorption coefficient, or SAC, which has been used as an optical monitoring parameter in traditional optical measurements, monitors only one wavelength. So when you buy a probe or you use a probe that measures SAC, you're getting a probe that monitors one wavelength, and then the user correlates the concentration of sample with the absorbance of that particular wavelength. Useful, but it could be better. Relating those absorbances, those wavelengths, to the electromagnetic spectrum, if we blow up the area in there between 100 and, say, 800 or so nanometers, we see that from 100 to 400 is the UV range, and in the range of interest for wastewater is 200 to 400 nanometers. Of course, that UV light is not detectable to the naked eye, but an instrument can detect it. Visible light, on the other hand, extends from 400 to roughly 900 nanometers, and that's where you can detect color and turbidity, for example. And in fact, visible light is the principle of a colorimeter. So if you have a colorimeter, you know that you take your sample, you add some chemistry to it, and in adding that chemistry, you generate a color. So by adding that chemistry, you're making it visible in the visible light area of the spectrum. What I'm talking about today really are sensors that are able to detect light absorption in the UV spectrum, and thus directly without the need for any chemicals. Taking a look at an example, this should look familiar to people out there. This is a BOD curve. So this is the BOD over time. So if we were to set up our BOD test and took samples at several BOD tests and took samples at regular intervals, measured the measure the DO and also the absorption spectrum for each of those samples, we'd find that at day 0, or when we started the test, we'd have a curve shaped like so on the top left. It would have relatively high absorbance, reflecting the absorbance from all the organic chemicals in the water. On day 5, which is the next chart over, which is in the bottom left, we'd see a similar shaped curve, only much lower absorbances. And this reflects that much of that organic contamination has been oxidized or consumed. And so there is less in the way of that optical path. So in Beer's law, the lower the concentration, the lower the intensity of the light. As we moved on past that 5 days, if we kept some bottles going, we would see that in 8 or 10 days or so, we might have a curve that look like the one in the middle, where the absorbance, there's actually a very high peak on the left-hand side around 200 and 225 nanometers. That is the area where nitrate absorbs. So you're getting nitrification in the bottle. Nitrate is going up. Of course, the organic contamination is going down, so very low signal from that. And then the last graph on the far right shows the sample absorbance totally dominated by nitrate, because that is the end product for that reaction in the bottle. And the organic contamination, having been converted to organic carbon to inorganic carbon, is very low. So the example here shows us that it's not only the magnitude of the absorbance in the sample over a range of wavelengths, it's also the shape of the curve that tells us how we should calculate that concentration. When it comes to design of an optical sensor, this example is for an optical spectral sensor. So let me explain a little bit what an optical spectral sensor is. An optical spectral sensor is a sensor that monitors, measures 256 wavelengths simultaneously. So unlike the SAC probe we talked about before, this probe is simultaneously measuring and continuously 256 wavelengths. And it does this with a lamp and a detector, recall the previous graphic we showed, inside the probe. And in observance of Lambert's law, that comes in, this particular version comes in 1 millimeter or 5 millimeter gaps, which are applicable to different applications. Recall that the longer the gap, the lower the intensity at the detector. Also, because we're monitoring so many wavelengths simultaneously, and so we're able to measure all those components in the wastewater, there are programmed calibrations. So this probe, for example, has calibrations for influent or untreated wastewater, mixed liquor, or effluent treated wastewater. And recall, each of those absorbance spectrums have a different shape and require a slightly different calibration. Other features of this probe are identical measurement and reference channels. Now, optical devices are superior to most other devices in terms of long-term stability and drift. However, optics do drift. And so built into the probe, behind the measuring gap, is an identical, in every way, reference channel that measures that decay in the optics over time, providing for a sensor that will last a long time and will give a very stable measurement. Also, ultra-clean ultrasonic cleaning technology is built into this probe. Basically, without wipers, it shakes the measurement window at a very fast rate to deter fouling. And then also the probe is very durable with sapphire measurement windows. Sapphire is a very hard material, and titanium probe body. So those last two features make the probe very durable. Now let's talk about applications for optical nitrate monitoring. Its main application is going to be for process control of nitrification and denitrification. So taking a look at this graphic right here, we can follow the path of nitrogen in wastewater. So in untreated wastewater, the nitrogen is mainly in the form of ammonia. Given the right conditions, those conditions being the addition of plenty of oxygen to supply the autotrophic nitrifying bacteria with enough oxygen to convert the ammonia first to nitrite and then to nitrate. At this point, we've converted our wastewater nitrogen from one form into another, but we really haven't removed much. Under different conditions, this time anoxic conditions, so anoxic is very low DO environment with nitrate, there are bacteria that, given heterotrophic bacteria, our run-of-the-mill bacteria that degrades our BOD, uses carbon to convert that nitrate first to nitrite and then to nitrogen gas, which bubbles out of the system, and the nitrogen is removed. So in a wastewater treatment plant, for example, or an activated sludge system, the three requirements we need are nitrate, which means we need good nitrification, conversion of that ammonia to nitrate. We require anoxic conditions, low DO, and we require a source of readily degradable carbon, which could be from the wastewater or from a chemical. In this flow sheet right here, all those conditions are provided at the very left side of the reactor. So we've got the nitrate from nitrification. So the return activated sludge, which has nitrate in it, and the internal recycle here, with even more nitrate in it, is returned back to the head of the tank, where it mixes with carbon in the wastewater. And then, since this area is not aerated, it needs to be mixed to keep that waste and bacteria in contact. So normally there's a mixer. So together, those conditions, we have the nitrate, which is recirculated from the end of the oxic zone. We have the carbon from the wastewater, and we have low DO by not aerating it. We can have denitrification occur. Now, some water resource reclamation facilities lack sufficient carbon in their raw wastewater for various reasons. And in this case, it may be necessary for them to add synthetic carbon to the wastewater in order to drive that reaction. I have a chart here from a customer who did a demonstration trial on an optical nitrate sensor. And we can see that the purple line is the online nitrate reading, and the orange line is the carbon dose. So what happens is the nitrate responds to the injection of carbon as it goes down. And this is an example of a carbon-limited facility. Now, as the carbon dosing increases, the nitrate concentration doesn't necessarily decrease. So at that point is where you would certainly want to curtail your carbon dosing to save the cost of the chemical. Our first customer profile is for the Met Council Minnesota wastewater utility. They have developed something called a Trak high DO nitrification tester. Let me explain. Their main goals are for aeration control and to operate at the lowest DO possible to save money. Makes sense. However, they still have nitrification limits year-round, and sometimes of the year those those ammonia limits are lower than others. So they need to keep their nitrifiers alive and active. So when they need them, they can put them right back into service. So what they do is they have this little box built into their aeration tank, and there's a pump and a mixed liquor pump and an air pump in here, which creates this mini reactor right in here, operated at very high DO. And essentially it's a respirometer. They're measuring nitrate continuously to assess the health of their nitrifiers. And so to show you a couple figures from that application that the customer shared with us, we have a couple different conditions. At high rate nitrification, they would expect that if the green line is the online nitrate, they would expect that once the batch started, that the nitrate would increase swiftly until it plateaued. Basically, all the ammonia were oxidized. And this is an example of a high rate by measuring the nitrate. On the other hand, they could experience a different situation with a lower rate. In this case, the nitrate is not increasing very fast, may not necessarily be a cause for them to take action, but they'd want to keep an eye on it. One action they could take was that if they found that their rate of nitrate generation, or in a different way of speaking, their rate of nitrification, or in another way of speaking, their nitrifying bacteria are in poor health or need a boost, they could choose to increase the DO concentration in their main reactor tank. And so this way they know they're always operating at the lowest possible dissolved oxygen concentration, and they're keeping their nitrifiers alive. In their words, the concept has been tried many times before by us and by others. It's just that this time it works with no maintenance. An adequate nitrate probe was needed. And so that was another important requirement for them, was a nitrate probe that was reliable and had low maintenance, because like many utilities, they have limited resources to take care of online monitoring equipment or any other equipment. Our second example is for denitrification monitoring at the Washington Suburban Sanitary Commission Seneca Wastewater Treatment Plant in suburban Washington, D.C. This is a slightly different configuration, but conforms to the same principles. They have a 4-stage Barden flow. So they have alternating anoxic and aerobic zones. The first anoxic zone is where wastewater carbon is used together with the return activated sludge and nitrate recycle from the first aerobic zone. So that nitrate, the carbon, and anoxic zones are created to denitrify. In the first aerobic zone, of course, nitrification occurs, increasing that nitrate concentration. The second anoxic and aerobic stages are needed to drive that nitrogen concentration even lower. So again, same thing happens. In the anoxic zone, that nitrate generated in the first aerobic zone is denitrified, and then the final aerobic stage is for polishing of any ammonia that might be generated in that anoxic stage. Carbon may be added in this second anoxic zone. As you can imagine, much of the wastewater carbon would be consumed by that time. More specifically for this customer, their goals were to achieve an effluent of less than 4 milligrams nitrogen per liter. That was their permit requirement. However, if they were able to achieve an effluent of less than 3 milligram nitrogen per liter, they would qualify for a $300,000 credit from the state of Maryland. Of course, they also wanted to minimize methanol dose. They could always just keep pumping carbon into that second anoxic zone to make sure they met their goals. But then it would offset the value of that credit. So what they've done is they have placed a nitrate sensor at the back end of their secondary anoxic zone, and they use it in a feedback control loop to control the carbon dosing at the front end of the second anoxic zone. And so fortunately for them, they have not really had to use much carbon. And they know that because their online monitoring tells them that they're at their target level, but if they did get above a level, they could activate that control loop and make sure that they continue to meet their goals. So what they've done is they've purchased 5 Nitrivis 701 TS probes, one for each of their 5 trains. And basically the reason for selection of this was the results of side-by-side trial with the competition. The things they liked about the Nitrivis were that it was easy to set up and easy to use, and especially a low maintenance cost. They didn't want anything with wipers. They knew the cost and hassle associated with having wipers. They're having very good success with keep the ultrasonic cleaning, keeping the fouling off. However, they did purchase supplemental air cleaning. They bought the MIQ-CHV valve module, which hooks right into their instrument air, and The sensor is programmed to blast air onto the sensor face at routine intervals. And the benefit of this, they found, was even though the ultrasonic cleaning was keeping the fouling off, say the biofouling, they were finding that hair and rags and other things were getting lodged in the measuring gap. And so the supplemental air cleaning effectively cleared those items that got stuck in there and gave them longer-term reliability. They still pull the probes out weekly to flush them out with a little water and take a look at them, but that's it. And so money is always an issue. Marty Johnson, the chief operator there, told me he has a boss too, and he had to sell him on why he needed the probes. He says, I have to have something that's reliable. This is the most reliable and easy to use equipment. We don't have to chase them around all the time to get them to work. Another example I want to provide is for New York City Department of Environmental Protection, Carbon Addition Project. This is yet another configuration. This is a step feed configuration. So it's a 4-pass, pass A, pass B, pass C, pass D, and each pass has an anoxic zone, noted by the orange, and an anoxic zone, or aerobic zone, noted by the blue. And so in the anoxic zone, the primary effluent and the nitrate mix together to denitrify the RAS in the first anoxic zone. Pass A then is aerobic, and it generates nitrate from nitrification, and so that nitrate then is denitrified in the Pass B anoxic zone, and so on and so forth. Their goals are to achieve an effluent total nitrogen of 7 to 8 milligrams per liter, and their control strategy is novel. They do monitoring of oxic zone nitrate, so they monitor the nitrate in the oxic zone just before the following anoxic zone for feed-forward control of carbon addition. And basically, feed-forward is a different strategy, and it involves some calculation of how much carbon to add. So they've also employed a biowind controller together with that online nitrate measurement to calculate the amount of carbon to add to the each step feed anoxic zone. They've really made a big investment in this with 63 NitroVis 701 IQ probes to be installed at 5 of their wastewater treatment plants, which are on sensitive watersheds and require relatively strict effluent nitrogen limits. So far what I've talked about is the traditional method of nitrification, denitrification. I want to talk to you now about a better way to remove nitrogen. So if we return to this chart where we show ammonia oxidation to nitrate and nitrate denitrification to nitrogen gas, requires a whole lot of oxygen and a whole lot of carbon to work. However, it's been discovered that we can shortcut this process through nitrite. So only part of the ammonia is oxidized to nitrite, and that ammonia and nitrite together is used to anaerobically oxidize the ammonia to nitrogen gas. And these bugs are autotrophic, so they do not require carbon. So substantial reduction in oxygen and carbon with this technology known as deammonification. And optical spectral sensors are particularly well suited to this application because they can resolve nitrate and nitrite separately. As you can see from this diagram right here, and you might expect that nitrate and nitrite have very similar absorption profiles. And so with a traditional one-wavelength sensor, there would be no way to differentiate one from the other. With a spectral sensor with wavelength sampling intervals of less than 1 nanometer, we can actually calculate the nitrate and the nitrate separately and display both. And so this shows a demonstration of how that works. This chart shows the online probe nitrite and nitrate measurement on the vertical axis versus the lab reference nitrite and nitrate on the horizontal axis for both the spectral nitrate measurement, the blue markers, and the spectral nitrite measurement, the red markers. And so if we had perfect agreement between the probe and the lab, all those measurements would fall perfectly on this 45-degree diagonal line. And we can see that's just about what happens. All the measurements are very close to that line, indicating very close agreement and very successful resolving of the nitrate and nitrite. There are a couple deammonification applications out there today. One of them is side stream treatment. This technology is in what is considered the early majority stage, in that it's been implemented in full scale at many, many facilities. So it's reached a status of maturity. Typically, the facilities that use this would have anaerobic digestion. Of course, the reject water after dewatering from anaerobically digested sludge has a lot of nitrogen and phosphorus. And so utilities, particularly utilities in areas that have strict nitrogen regulations, are finding that it's beneficial to deal with that nitrogen in the side stream and treat it with deammonification, then to return it to the mainstream and treat it with traditional denitrification. The other application is for mainstream, and this would be implementation of deammonification in the main wastewater treatment processing steps. This is at the demonstration stage. However, Alexandria Renew Enterprises is going to launch their first of its kind mainstream deammonification system in 2016 using YSI IQ SensorNet spectral probes. In this picture right here is a NYCDEP NI701 installed in one of the Alexandria's bioreactors. Of course, it's on a pole mount here below the water in the mixed liquor. The motivations for wanting to implement deammonification mainstream is twofold. One is for energy savings. Of course, we don't have to put in nearly as much oxygen as shown in the chart on the previous page, but also sustainability. This process gives the utility a much lower carbon footprint because in addition to the reduced energy requirement, they no longer need to import sources of synthetic carbon to inject into the process. Recall, this is an autotrophic process that uses inorganic carbon, not organic carbon. Well, it's really a good time to monitor nitrate, and we have two very good options for that. And I'm going to compare and contrast a little bit optical nitrate monitoring versus ion selective electrode nitrate monitoring. First off is cleaning. That's an important step for any online probe. With the ISE, you have to be fairly careful of the water you use. You don't want to use DI water, for example. Processed water is best. But a soft bristle brush, and you wipe them off, and it's not a whole lot of effort. With an optical probe, a little less particular. You don't have to use processed water. In fact, it's discouraged. And you can, in fact, use chemicals to clean the optical measuring windows. What's shown here is something that YSI offers. It's a cleaning card. Basically, it's a felted, stiff card that you can use to floss the measuring windows. Basically, this is a push. Cleaning is required for both, but cleaning is just a little bit different for each, ISE and optical. When it comes to calibration, this is when things start to diverge. With the ISE technology, you need to you measure nitrate and chloride, and the chloride is for compensation because the nitrate measurement device is not perfect. Some of that chloride actually is measured as nitrate. And so what's required is something called a matrix adjustment at commissioning, and typically every 1 to 3 months thereafter. For an optical probe, it's really only necessary to monitor or measure separately nitrate. Chloride does not occur at high enough concentrations in a municipal wastewater to cause an interference. However, a user calibration for nitrate can be done at commissioning. And I have that asterisk there. While there is a factory calibration, and it wouldn't be unusual for the probe to work right out of the box, a user calibration can be performed to improve the accuracy of that factory calibration. Or if you have a single wavelength probe, you would, of course, would also have to do a user calibration for that no matter what. But longer term, you probably may not need to repeat that calibration, or at the very least, you'll repeat it very infrequently. Next comparison I have here is with consumables. The ISE probe shown here, and you can kind of see the exploded view there of the electrode sticking out. Those electrodes eventually deplete and need to be replaced. And so electrode replacement is an important factor with an ISE. Typically, we recommend for our electrodes that they be replaced every 12 to 24 months. With an optical probe, I've deliberately shown an empty box. And that's because with at least the IQ SensorNet nitrate probe, at least, there are no consumables, no wipers to replace, no electrodes, of course. All that's required is for the customer to do that routine cleaning step when necessary. Performance, of course, you're interested. You want to know about that. How does the performance compare between optical and ISE style probes? Well, starting with the measuring range, optical probes measure pretty high nitrates, suitable for most municipal wastewaters. An ISE has an advantage there in that it can go up to 1,000 milligram nitrogen per liter. So in some applications, that's going to be important. Resolution, in that case, optical has that beat. It has up to a 10-fold higher resolution than the ISE. And this means that the optical may perform better at lower concentrations, especially concentrations less than 2 milligram per liter. Pressure resistance, not a whole lot of difference there. Power consumption, again, the optical consumes 8 watts, up to 8 watts, partly because of the cleaning system operation, partly because of the lamp. Response time, the ISE has a fast response time. We say spec less than 3 minutes. With the optical probe, it's programmable. While the measurement updates every minute, most customers will choose to program in a longer response time to smooth out the measurement. Temperature, the optical probe does not have a separate temperature measurement. The ISE probe does have a separate temperature measurement. As far as additional parameters per probe, the optical can do, for example, COD, BOD, TOC, nitrite, and TSS. With ours, you get up to 5 measurements per probe. ISE, on the other hand, in addition to nitrate, you can also get something that monitors ammonium, potassium, and chloride. The big difference there is the ammonium. If you need the ammonium, ISE might be your bet. Warranty is the same for both, 2 years. I do want to point out, though, that the warranty of the electrodes, oops, I got these two mixed up. There are no electrodes in an optical probe, but the electrodes for an ISE warranty is 1 year. So I apologize for that. The NA should be under the optical column, and the 1 year should be under the ISE. So when it comes to thinking about what nitrate sensor you might want for your application, remember that you have 2 gap sizes, 1 millimeter and 5 millimeter. The 1 millimeter is for high concentrations, and the 5 millimeter is for lower concentrations. The Nitrivis monitors nitrate and TSS. The Nitrivis NI, nitrate and nitrite. Likewise, the NYCDEP NI also does nitrate, nitrite, and COD, BOD, TOC. We offer a single wavelength probe for nitrogen monitoring. That's the NOx probe. And so it monitors kind of a combination of nitrite and nitrate. And for a lot of customers, that's sufficient. They just want to know what that is, whether that nitrate plus nitrite is what that is. Really, for traditional denitrification, bacteria will use the nitrate just as readily as they will the nitrate. Then I've also thrown in there at the bottom the CarboVis, which of course does not do any nitrate, but I wanted you to see that it's also possible to just monitor the organic carbon with the TSS. Well, that concludes the content of the webinar, but we do have time for questions. I want to remind you that if you're planning to be in Denver, July 10th through 12th for the WEF IWA Nutrient Removal and Recovery Conference. That is a really terrific show, very targeted towards nutrient topics. We're going to be there with our booth. Look forward to seeing you there if you can make it. Also, you can find resources for IQ SensorNet and YSI on the web through SlideShare, YouTube, and of course, telephone and email. So please feel free to check out these resources. But now I think I'm going to take the rest of the hour to answer some questions. Thanks for your attention.
Thank you, Rob. Okay, now I think we have some questions coming in here, so we will start asking Dr. Rob some of these questions. First of all, how do you decide which nitrate monitoring technology is best for a particular application?
Yeah, that's an important thing to decide, isn't it? As I mentioned, it's real easy if you have to measure very high concentrations of nitrate because you get a higher measuring range up to 1,000. But even more so, I think even if you're monitoring on the higher end of those nitrate concentrations, you might choose to go with an ISE simply because it's less expensive. At least it's less expensive to purchase. However, if you need the most reliable measurement with the least effort, no matter what, you're probably going to want to go with spend the extra money and get the optical nitrate probe. It's especially going to be most effective at measuring low nitrate concentrations.
Great, thank you. Does an optical nitrate sensor work well at low concentrations of nitrate?
Well, yeah, I guess I kind of started with that, answered that question a little bit with the previous question. It does, in fact. I would not expect its performance doesn't. The knack against ion selective electrodes has been its performance at low concentrations, and it's earned. I mean, there are applications where the ISE is especially going to be challenging at low concentrations. The nitrate, on the other hand, doesn't suffer the same limitations and should work perfectly well below 0.5 milligram nitrogen per liter or even lower.
Okay, what are the advisable locations for the nitrate probes?
See, a lot of our, with denitrification, there are two most effective locations for nitrate monitoring. One is at the end of the oxic zone. So if you think of the configuration that I showed you early on with the anoxic zone followed by the oxic zone, by monitoring the oxic zone nitrate, you're getting an idea of how well your treatment's doing. Are you meeting your goals? And however, the anoxic nitrate is very important. Measuring nitrate at the end of the anoxic zone is very important, especially if you're going to dose carbon, because the anoxic zone nitrate tells you really gives you an indication of whether you're carbon limited or nitrate limited. And those two measurements tell you what is the appropriate process control response. So for example, we talked about carbon addition here, and that's true, that's effective control for nitrate, but mixed liquor recirculation is the other thing for control of denitrification. So if you compared the nitrate readings between the oxic and the anoxic nitrate, you could decide which is the appropriate process control adjustment to take. Increase or decrease the carbon dosing, or increase or decrease the mixed liquor recirculation.
Okay, the next question. What are the calibration verification methods for the optical nitrate probe?
Yeah, hey, that's an important thing to know. You know, you buy your probe, you put it in the water, and we always encourage our customers to convince themselves it's working properly. So whether it's ISE or the optical nitrate, colorimetric methods are suitable to verify the reading. And with nitrate, it's a little tricky because you've got quite a few choices. We have found that the cadmium reduction method is less reliable in municipal wastewater than the alternative, which is the chromotropic acid colorimetric method. Basically, both of them are very simple to do with colorimetry, but the chromotropic is more reliable.
Okay, next question. Does this probe have memory, and how much memory?
Yeah, so really the memory has more to do with the IQ SensorNet. So we have data logging with our, if you purchase the probe with the 2020 XT controller, which is typically the most common application, it has substantial memory capacity. So you can set up data logging and record that measurement on the controller. And then you can either view it on the screen or with a USB stick, download that data in a CSV format so you can look at on your PC. Alternatively, the system has output modules, so you could send, for example, a 4-to-20 recorder output out to your SCADA system and record the data and view the data that way. So you've got really two choices.
Great, thanks, Rob. Actually, we've got a few questions about the sharing the presentation, so I'll go ahead and field that question. The presentation will be made available via SlideShare, and it will also, the recording, a link to the recording will be sent to you within 2 days after the webinar. So you can either view the recording or go to YSI's SlideShare page and access the slides via SlideShare. Okay, is there any rule of thumb on how many sensors can be placed based on MGD, flow, or basin size?
Buy as many as you can possibly afford. No, just kidding. You know, it's not really simple to judge it based on, you know, the volume of the basin or the flow rate. The important thing is really what are your objectives. In our example for Washington Suburban Sanitary Commission, they had 5 trains and they needed to very carefully control each train, the carbon dosing for each train, so they bought 1 probe per train. But another customer might decide, maybe that didn't have as tight limits, might decide to monitor not every train, but maybe a train or 2, and then kind of mimic the control for the other trains the same way. So it also depends on your ability to actually implement any process control. Many utilities maybe lack sufficient control points. For example, dissolved oxygen. If you've only got 1 drop leg or 1 sensor grid to control, maybe it doesn't make sense to monitor with a bunch of sensors. But that's also a consideration is what your control capability is. But that's going to be something that's going to be probably more on a case-by-case basis.
Okay, for measuring nitrate at a wellhead, do you have a jacket to catch or measure the nitrate in a side stream?
Yeah, so I guess you're getting outside of municipal wastewater here. That's okay. Nitrate and nitrite, we have had success monitoring those optically in, for example, groundwater applications. And in this case, we offer, for the type of sampling you're suggesting, we offer a flow cell. So basically, the probe, the measuring area, the probe would be put in this sleeve, which is a flow cell. You would have to get sample to the flow cell and, of course, have a place for that sample volume to be discarded. But and we have a number of different. Well, actually, for the nitrate sensors, we have really only one flow cell type. I don't have the specific details there, but if you contact YSI, we can set you up with the flow cell equipment you'll need.
Okay. You mentioned a link to SCADA. Can it also transmit to the internet?
Yes, in fact it can, and it's not really a function of the probe. Again, this is going to be a function of the IQ sensor net. We have a particular module that will you'll be able to put your system on the internet, and that module is called an MC2 module. Basically, you would need to provide some of the hardware, and you might need a static IP, but absolutely, it's very easy to set that up.
Okay, I think we have time for maybe one more question. What is the typical cost of the YSI optical probe, and what would be the life of the probe?
Yes, this is. I was wondering how long it was going to take you to ask me that. Yeah, well, the optical nitrate probe depends on which one you order. The most fully functioned nitrate probe is going to be close to, and that would be with the COD BOD measurement with nitrite measurement, would be close to $20,000. However, if you were interested on the lower end, maybe if you just wanted to monitor nitrate or just NOx, you'd be closer to $12,000 as a list price. Now, to contrast that with an ISE, which is your other option, an ISE just for nitrate is going to cost from us a list price of around $5,000. Actually, probably a little less than that. So there is a significant price difference depending on what it is you want to monitor. But as far as ownership costs go, like I said, there's really there's no consumables for the nitrate probe, and I think the other part of this question was how long, what's the lifespan, and really I don't know. I don't know that we've had any. Possibly we have, but I don't know that we've had any that come back because they've just exceeded their lifetime. The only thing that might go on that is the lamp, and what I was told is the lamp lifetime is just absurd. I mean, it's way beyond what you're probably going to need. In fact, you're probably going to upgrade your technology before the lamp goes. So, and then the other part of the question, I think we talked about how the unit is calibrated. So, yeah, so that's some ballpark numbers on costs and lifetime.
Well, thank you, Dr. Rob. Well, that wraps up today's webinar. We appreciate you attending, and we hope that you found all this great information useful. Please take a few minutes to complete the brief survey and let us know how we can better serve you. We really appreciate all the great questions today. If we were unable to answer your question, we will follow up with you directly with answers. So once again, thank you, and we hope to see you at the next webinar.